problem with the U substitution notation. So if you didn't like that, here's your chance to try and get it one more time. Alright, 5.6. Definite integral substitutions. So U sub with limits of integration now. And also we're going to talk about areas between two curves. Those are cool. So how do we utilize U substitution for a definite integral? Well, we're going to look at two different ways. I'm just going to show you. So first of all, let's do it the way that I think most of you have been doing it without the U. How we would deal with the limits of integration. And then we'll go and deal with it with the U notation. So first of all, you need the antiderivative. Well, take the antiderivative. You need to look for the chain rule part, the big messy part. Well, that would be the square root. The inside of the square root is x cubed. Well, that's cool. I'm going to start using a new U notation just to help y'all out. So I'm going to relate the U to what I've been doing. So that means this is going to be your U. Well, what is the derivative of that? What's the du? Well, the corresponding du, derivative of x cubed plus 1, would be 3x squared dx. Well, that is actually perfectly right there. Cool. So, using what we've been doing, we would integrate this and write the antiderivative, which would just be taking care of that square root. Oh, shoot, I forgot to rewrite it. All right, algebra. We need to get rid of the square root notation to find the antiderivative. That'd be easier. So, square root, rewrite as a power. Now we're ready for the antiderivative. So again, this is your du. And then inside here is your u. Using what we've been doing, we would take the antiderivative by doing the power rule. So x cubed plus 1. Add 1 to the power, so it would be 3 halves. And put the reciprocal in front. Limits of integration, go at the back. So from -1 to +1. Plug it in. Plug in the 1 first, the upper limit of integration. So 2/3. You can actually let that chill out front and multiply by everything later, or you can leave it as part of your problem. Really up to you. If I plug in the 1, I get 1 cubed plus 1, so that is 2 to the 3 halves. Minus, if I plug in a -1, 2/3 is still there. -1 cubed is -1, plus 1 would be 0. So that all zeroes out. End up with 2/3 times, what is 2 to the 3 halves really? Well, it's really square root of 2 cubed. Now, in my lab, it's probably going to make you simplify this. Let me remind you, to take the square root, you have to take out a pair of 2's out of the square root. You only write one of them representing the square root of that pair. We already have the 2/3. We have 3 2's inside, so I'm going to take 2 of them, pull them out, and only write 1. That leaves us 1 left inside. So, simplified version here would be the 2's outside multiplied together, square root of 2 is stuck inside, and a 3 on the bottom. There you go. So we're going to do the same problem again, but now we're going to do it with a U notation. And we're going to transform our limits of integration. What do I mean? Well, these limits of integration in the original problem, because it says dx at the end, these are x values. So x equals -1, all the way to x equals +1 are our limits of integration. Well, what we're going to do is we're going to rewrite our integral using U notation. So u, like we said earlier, is the inside of our cube root, and du is going to be the 3x squared dx. So our integral becomes, don't write the -1 and 1, those are x values. So the square root of, well, we call the inside of that u, and the rest of it, 3x squared, and it up. 3x squared dx, all the rest of this is just du. So that's what we're really integrating if we switch to U notation. But now we got to change our limits of integration. So originally we integrated from x equals 1 to x equals -1 to x equals +1. We had to change these to the corresponding U values. So the corresponding U value, we just use our formula for U. We need to cube the x and add 1. So 1 cubed plus 1, that's going to be 1 plus 1 is 2. So our upper limit was x equals 1, the corresponding U is a 2. So we put that at the top of our limit of integration. When x equals -1, we have u equals -1 cubed plus 1, or -1 plus 1, a 0. Well, it's at the bottom. Make sure whichever x you evaluate and change to a u, you put in the same position, you put the corresponding u. So sometimes these values are going to be backwards, meaning the big number on the bottom, the small number on top, but that's okay. Whatever x was, change it to a u and put it in the same position. Don't switch them around. Alright, so let's integrate this. So we're integrating from 0 to 2. Again, we don't like doing roots, so write it as a power. U to 1/2 du. So you can power both backwards. So we add 1, we get 3/2. Up front we put the reciprocal. Evaluate this from 0 to 2. So we plug in the top one first. So 2/3 times 2 to the 3/2 minus, if you plug in 0, it all zeroes out. You're going to simplify this once. Do it again, we'll still get the same 3. Same thing. 4 square root of 2 over 3. So there are two techniques here in order to do definite integrals involving a u sub. It's your choice. You can stick with x's all the way through, or you can switch to u and change everything to u, including your limits of integration. Alright, let's try some more. I'm going to focus on the u sub notation. I'm going to let y'all use the other video I made to practice the x notation. Alright, so use the method of transforming the limits of integration to evaluate the following. So first of all, we got to figure out u. Well, we have cotangent and cosecant. We really haven't done all that much with those, so what I would like to try is to try and get rid of those. So, see if I remember what cotangent is equal to. You could say 1 over tangent, but I really don't like 1 over tangent any more than I like the other one. Actually, yeah, I don't like that. So, we'll switch it to sines and cosines. So, tangent is sine over cosine, so cotangent would be cosine of a sine. And then cosecant squared, so let's write cosecant. So cosecant is 1 over sine. Wow, my brain froze there for a second. Alright, let's see if doing this substitution, this is not u sub, this is just like trig identities, trying to clean up our integral. If we use this substitution, does that help transform it into something that's nicer? So cotangent we replace with cosine of theta over sine of theta. And cosecant we replace with 1 over sine, but we have to square it because the cosecant was squared. Hey, we can put the sines together. So this would be cosine of theta. And on the bottom we have sine cubed. But I actually want to bring that up. If we bring sine cubed up, it's actually going to be sine to the -3. And you can put the -3 here or outside the parentheses, it's up to you. Outside is usually clearer in order to figure out who our u is going to be. Don't forget your d theta. Alright, so with this in mind, new way of writing out the problem, sines and cosines are just easier and more natural for us. Let's write down what u would be. So, u is the inside of the complicated part. So sine in the power, that's the complicated part. The inside is the sine. So then we need du. So the derivative of sine is cosine d theta. And let's see, does that work? So cosine of theta d theta, all of that is our du. Yeah, everything's going to change to u. Remember, your limits of integration are going to change. Just check and make sure everything else works before we worry about that. So cosine of theta d theta, that becomes our du. And sine of theta to the -3, that's u to the -3. Hey, everything changed to u. So now, we take the time to change our limits of integration. So, originally we had theta equals pi over 2. That corresponds to u equals sine of pi over 2. Don't plug that in up there. Evaluate. What's sine of pi over 2? Well, that's straight up on the circle, which we want. And theta was pi over 4 at a lower limit of integration, so the corresponding sine of pi over 4 would be square root of 2 over 2. So our limits of integration, the bottom became square root of antiderivative of u to the negative 3. That would be add 1 to the power, multiply by the reciprocal, and evaluate from square root of 2 over 2 to 1. I'm going to leave that negative 1 half out front. Just worry about the rest of it. So if we plug, so basically I'm doing this here. Negative 1 half out front, we worry about the rest. Alright, so if we plug in 1, let's rewrite this. U to the negative 2 really 1 over u squared. So now, if I plug in 1 over 1 squared would just be 1, minus, if I plug in the square root of 2 over 2. Okay. So you gotta square it and you gotta flip it over. Let's just work that one out. So 1 over square root of 2 over 2 all squared. So 1 over, let's see, square root cancels the square for the top part. You still gotta square the bottom, so that would be 4. So that's, flip it over, 4 over 2, or 2. Whoops, what am I writing on here? 2. Alright, so negative 1 half out front. Inside we end up with a negative 1, so the final answer is 1 half. There we go. Alright. One more. Alright. The integral of tangent is actually a special case. I think I've already done this in one video, but I could be wrong, so we're going to do it here all the way through. So tangent, we don't know what the antiderivative is, because what we have talked about is the antiderivative of secant squared and the antiderivative of secant tangent. That's not what we have here. So what we have to do is we have to rewrite this as sine and cosine to see if there's something in that format that will allow us to find the antiderivative. So negative pi over 4, positive pi over 4. Tangent of x is the same as sine of x over cosine of x. Yes. Well, let's break this up. We need the complicated part, like the chain rule part, the inside-outside part, separate from everything else. So if I look at this and I see a fraction, and in the denominator of the fraction I see cosine. So I'm going to think of that as the inside-outside part. So sine of x we're going to leave separate, times 1 over cosine of x. Cool. Alright, so if I look at the fraction, cosine is the inside because it's in the denominator. So let's let u equal cosine of x. Then du, derivative of cosine, negative sine of x. Now if you want to fix your problem you can, or you can solve for what you have and plug it. I'm just going to fix it. That's going to be easier for you all. That's what we've been doing most of the time. So I need a negative sine of x, so I'm going to put the negative there, and I'm going to make up for it. So negative sine of x dx. All that is my du. And then 1 over cosine is my 1 over u. Oh, don't forget the negative in front. Everything changed to u's. So we're good. Now that we know that our u sub is good, we're going to change our x's. So x was negative pi over 4 to positive pi over 4. So negative pi over 4, we plug that into our u, the cosine of negative pi over 4. So that's in the fourth quadrant, so cosine is positive in the fourth quadrant, and that would be square root of 2 over 2. For pi over 4, cosine of pi over 4 is first quadrant, cosine is still positive, so it's also square root of 2 over 2. So our limits of integration are from square root of 2 over 2 to positive square root of 2 over 2. Wait a second. Think about this. We're integrating from one value to itself. What does that mean? That means that this whole thing has to equal 0. Remember, this is one of those integration rules. You integrate over nothing from one number to itself. There's no area there. You have to integrate over an integral to get an area. So because there's no area, you have no value. 0. If you want to continue and find the antiderivative, plug in your limits of integration, put the negative in front, you can, you'll still end up with 0. Could we have seen that from the beginning? Actually, yes, and this is what we're going to talk about. Tangent is special. Let me draw a rough picture structure of tangent. So we from negative pi over 2 asymptote to pi over 2 asymptote. Our curve is this. So this is what we call an odd function. An odd function is very special because it's symmetric across the origin, meaning the area from negative pi over 4 to positive pi over 4 is opposite of each other. We have a negative area on the left side of the x-axis, y-axis, negative area on the left side, positive area on the right side. They're the same size area because they're symmetric. Because of the same size area but opposite signs, they cancel each other out. And that is what we're going to talk about here. So, let f be continuous on a symmetric interval. So from negative a to positive a. It has to be symmetric about the y-axis. Part A. If f is even, so an even means it's symmetric across, symmetric across the y-axis. And if f is odd, that means you're symmetric across the origin. Meaning, if you flip your curve across the x and across the y, you both flips, you'll end up with the original picture again. Or, you see here that these two are opposites. They're diagonal across the origin. Another way to kind of see it. Alright, so if f is even, you have this scenario here where the two sides of our picture are going to be the same area. So what you can do is, instead of integrating the entire interval, just integrate from 0 to one side. And then double it. So, part A says, you see that your graph is symmetric across the y-axis, meaning the left and the right are mirror images. Then you only need to find half of your area, and then multiply times 2. That would give you the same thing as if you found all of the areas, so negative a to positive. Part B here, f is odd, second picture here we have. F is odd, then you integrate, you're going to end up with the symmetric areas having opposite sides, canceling each other out. So this is a positive area, this is the equivalent negative. This is a positive area, this is the equivalent negative area. All of those cancel out, causing you to have a total of 0 in your integral. This is not a total area question. Total area, you would make them all positive and add them all up. This is what is the integral value. The integral ignores the area being positive or negative. It just takes all the positive areas, finds all the negative areas, adds them together with the negatives included. So be careful with that. If you're asked for a total area problem, you have to break it down. This is only applicable if you have an even or an odd function and you're integrating from negative a to positive. Only times you can use this. So here's an example. So I showed you an odd, that was a tangent. This is actually an even function. How do I know this is even? If I were to put negative values in any one of these three positions, they all would end up becoming positive. Why? If I do negative x to the fourth, it's an even power. That would be positive. If I do negative x plugged in here, it has an even power. It would be 4x squared. Yes, there's a negative in front, but the negative I plug in is gone. Didn't do anything. Plus 6. Well, there's nowhere to actually plug a negative in there, so that would still be positive. So because plugging in negative x did not change the function, that's why this is even. Basically, make sure everybody has even powers. That's really the easiest way. A constant is always even. Because it will never change its sign due to a negative being plugged in. So it's always going to be what it is. Alright, so what do? Well, to evaluate an even function, we don't have to go from negative 2 to 2. We can just do half of it. So go from 0 to 2. So if you only do half of an even function, you have to then double your answer. We're going to do that. What's the benefit? Well, like I told you before, zeros are our friends when it comes to definite integrals. Most of the time when you plug a zero, stuff disappears. That's the benefit of this trick. At least for our rules. Alright, so 2 times. What is the antiderivative here? So x to the 5th times 1 over 5 minus 4 4x to the add 1, so 3 divided by the 3 plus 6x. We're evaluating from 0 to 2. Plug in the 2 first. So 2 times, plug in 2. 2 to the 5th, 32 over 5. Minus 4 over 3 times 2 cubed would be 8. Plus 6 times 2 is 12. That's what we would plug in 2. Minus, we plug in 0, well everything zeroes out, it's all gone. So 2 times 32 over 5 minus 32 over 3 plus 12 over 1. Alright, so let's make the denominators common, so that would be 15. Can't reduce anything? Nope, I don't think so. Let's just do the first 2 terms, and then we'll worry about the last one. So we need to multiply the first one, top and bottom, by 3 to get our LCD. Second one by 5 to get our LCD. 3 times 32 would be 96 over 15, minus 32 times 5 would be 60 over 15, plus 12 over 1. Hoping it reduces, and then I don't have to do as big a denominator, but it could be wrong. So 96 minus 160, that would be negative 64 over 15. Cannot be reduced by 3 or 5. So the 12, we have to get a common denominator. So multiply top and bottom by 15. So that would be 80 over 15. 2 times 116 over 15 times 2, so 232 over 15. Those fractions. I already forgot what we were doing. Oh yeah, even. Okay, so then that would be the integral, because this is an integral.